This tutorial is to further explain some of the concepts within the chapter on modularization. So I'll go ahead and pick up where I just left off. And the last thing I talked about was black box and white box testing. Next thing I've got here is the stopping case. And the stopping case, really, you can't understand it just by looking at the word. It has to do with recursion. I'm afraid I'm going to have to show you an example of recursion. There's almost no way of doing this. I don't really expect you at this point to understand very much about recursion, other than if you see it, you know what's going on. So I'm going to create a recursive function called my recursive function. And I'm going to say that you are going to come in with a value, say, of 5. Now, I'll copy that, and I'll come up here, and I'll make this a void function, and I'll say that you're coming in with an int. That looks good. Let me go ahead now and copy that prototype, and I'll move down below. So I'll just say this value that you're coming in with is some value int d. And all I'm going to do here is I will say if d is greater than 0, we're going to call my recursive function with d minus 1, and in the meantime I'm going to say cout d. Let me put a space after this, so I'll say quote space unquote semicolon. And then up here within my main, I'll go ahead and I'll call that function. Actually, I may have already done that. I did. My recursive function. So here's what's going to happen, and this is what recursion is all about. I got my prototype, I got my call, I got my function. We come in with a value of 5. That's the first thing I come in with. Do I meet the condition? Is d greater than 0? You bet. I'm in. I call this function. What's the name of this function? My recursive function. What function is that? That's the function that I'm in. I'm calling the same function that I'm in. And that is what recursion is. Recursion is where you have a function call itself. And it will do this just fine. It'll allow me to call itself. So I get to this line, I'm calling this function. I get to this line, I call this function. I get to this line, I call this function. It can have the effect of looking an awful lot like a loop. So I get into here. I then call the function, but what was 5 before becomes a what? D minus 1. If it was 5 before, if D was 5, what is D going to become now? 4. Yeah, that's what it's doing. It's actually going down by 1. And then I call myself again. So is D less than 0? Sure it is. It's a 4 now. I then get to here. What's D going to be equal to now in the call? A 3. I go back through here. Is 3 greater than 0? You bet. So I get down to here. What am I sending in now if D is a 3? I send in a 2. I then come back up here. Is 2 greater than 0? Sure. I take 2 minus 1. I'm down to 1. Is 1 greater than 0? Sure, I get in. Okay, I come up to here with a 0. Is 0 greater than 0? No. So I just come down to here. Now here's the interesting thing. As I get these numbers, you kind of have a picture in your head where they kind of back up 5, 4, 3, 2, 1, and I'm not allowed to output them. The very first one that's going to be outputted, as you guys can see, is the 0. Can you see that? So what you've just created is something called a stack. You've probably never heard of a stack before. I mean, you might have in the English language, but what's going on is I come in with a 5, and then on top of that, I put a 4, and then on top of that, I come in with a 3, and then on top of that, I come in with a 2, and on top of that, I come in with a 1, and then on top of that, I come in with a 0. Well, good news, you're not really too responsible for this, but you just need to know what a stack is. What happens is everything backs up, and whatever is the last thing on, it has to be moved off before you can get to anything below it. So even though I came in with the numbers that were 5, 4, 3, 2, 1, when I come out with them, if I'm doing the output after the recursive call, I'm going to see the numbers outputted as 0, 1, 2, 3, 4, 5. Everything gets reversed. Does that make sense? That is what happens a lot within recursion. I'll go ahead and rebuild this and run it, and you can see that's exactly what I got, 0, 1, 2, 3, 4. The interesting thing about this is if you do the output beforehand, it reflects the order with which the numbers are coming in, so you will see the 5, 4, 3, 2, 1, because that really is the order the numbers come in with. It's just then they get plugged up, and they can't get past the recursive call. So this is really cool. This is one of the easiest ways I can think of reversing everything that's coming in. Recursion is a very powerful tool, and there is a whole chapter later in your book devoted to this topic, but right now, we're not going to worry about that too much. Okay, so going back to our notes, the only reason why I had to show you that is what is the stopping case? The stopping case here is where D hits 0. We're not allowed to have values which are equal to or less than 0. That would be the stopping case for D. So that's why I had to bring it up. It actually comes up in your book, and it doesn't make a lot of sense that it's discussed here. Unwinding the recursion. You just saw the example of unwinding the recursion. We come in with the values 5, 4, 3, 2, 1. It gets backed up as 0, 1, 2, 3, 4, 5. When you see those values, we're no longer having this condition met. Things are not being backed up. And when we output the values here using the cout statement, we're actually unwinding all the data that has been plugged up. That's really what we're doing. So that's what we're talking about, unwinding the data. Cohesion. Cohesion refers to what functions are doing. If you make really good functions, the idea of a good function is do one thing and do it well. If you're a function, you're made to do two different jobs, you're kind of splitting your activities. You probably know as a person when you're asked to do two things at once, you start to mess things up. That's not very cohesive. Cohesive means you've got one job and you just do that one job. Ideally, that's the way we want to make our functions. Don't do two or more things at the same time. So if I mention this word cohesion, that's what I'm talking about. Scope comes up a little bit when you're talking about functions. Scope has to do with how far you can see a variable, how far can you see a function. Functions can also be seen a long way off, and within a function you can make them pretty local to, say, your main. You can put them in a class and actually give them quite a bit of scope. So scope just refers to how far you can see things. And usually when you see this term, we're usually thinking about variables. Like if you put it between a set of braces, a variable becomes local to those braces. If you put it in a for loop, it becomes local to the for loop. If you put it within a function and you don't declare it as global, it's going to be local to that function. You're not going to see it anywhere else. You can have two variables with the same name and two different functions. It's perfectly legal. Just like in our society, you can have two people with the same name living in two different towns. There's nothing wrong with that. Okay, and they all have their own value and everything else, but they are not the same variable. They're treated as different variables, and when you have that's local. If you declare a variable up at the top of your program, up here, you can actually make a variable which would be global to your function. So if I say int my global variable, and I set it equal to a value, I say it's equal to the number 8. This is perfectly illegal. You can do it, but it's a practice which we discourage within computer science because this variable now, since it can be seen in your main method as well as any other methods that you have here, functions that you have here. I'm using functions and the word method interchangeably. It's actually functions is the best term. A method is actually a function within a class. So let's refer to these as functions. But anyway, right here within order to variables, if I said C out here, my global variable, I would be able to see what my global variable was. I would actually see that output. I could take that same line and I would also know what my global variable is down here in my recursive function. I also know what it is up here in my main. So because I can see it everywhere throughout my program, that's why we're saying it's global, and that's really a bad idea for a variable because not only can I see what it is, I can change it in any one of those functions. I also might be making functions which are dependent on global variables, and one of the ideas you want to have when you make a function is you don't want to make it dependent on anything. You want to make it stand alone. It should not be dependent on somebody's crazy global variable someplace to use information. If you need to pass information to a function, you should always do it through its parameters. So never rely on global variables. Now the one exception to this is if you create this as a constant. I could say const pi is equal to 3.14. I need to define what the data type is. It is a double. Now, a lot of people would say it's okay to have a variable like pi, which is a constant, declare it global. But even here, I have a little bit of an issue in this, in that if you go into your functions, you're actually making them dependent on a global variable or a global constant that you've declared within your program. So if you could rely on this pi, you wouldn't have any idea if somebody would know that they could depend on it or not, or I wouldn't be able to take, say, a function that depended on it and paste it in somebody else's program without declaring this constant first. So it kind of creates an issue too. Now we're going to say that constants are okay. I'm not going to discourage the use of constants, but I am going to discourage the use of global variables. Don't use them unless they solve a tremendous problem. And to be honest, in some of your higher level courses, sometimes you're going to get into such terrible issues that this will be the only way that you'll do it. And your instructors will be a little bit tolerant of it in most cases. Some cases they won't. They'll jump your case. So you always need to use best practices wherever possible. So anyway, that's a nice example of scope. A global variable has a lot of scope. A local variable like A here has very limited scope between this brace and this brace right here. So other functions can be called A, but they would be different variables within my program. Going on, the next thing I've got here is prime numbers. I only discuss it here because you use it in one of your labs. Prime numbers are numbers which are only divisible by 1 in itself. I have a section here on factorials. Factorial is where you write down a number, any number, which is an integer, that's positive or equal to 0, and then you write all the numbers descending down to that value. There's one thing I should say here. There's a few things some people don't know. If I write, say, 4, obviously the implication of this is that 4 factorial is equal to, what is 4 factorial equal to, guys? Somebody tell me, what are the numbers I have to multiply? 4 times 3 times 2 times 1. And obviously that is going to be 4 times 3 is 12, times 2 is 24, times 1, that's just equal to 24. What is 0 factorial equal to? What is it? This is going to surprise you. 0 factorial is equal to 1. One of those strange little quirks in mathematics, so just be aware of it. Negative numbers you can never raise to a factorial. Okay? So just be aware of that. Let's go back to our notes. So you've had factorial defined. The next thing you have to know is what a factor is, and from your math class, you just simply know that any number that divides into another number is a factor. So if I looked at the factors, say a 12, the factors of 12 would be a 1 divides into 12, a 2 divides into a 12, a 3 divides into 12, so does a 4, so does a 6, so does a 12 itself. So all of those numbers are factors of 12. Okay, a module is just a function if we're talking about a computer program. Modularization is making things from parts, so we're making things with functions. Recursion, I've already explained to you, is where a function calls itself. A side effect is a change in a value of a variable from its last iteration or the result of the last update. You should know what side effect is from the last chapter where we were dealing with loops. Now, that gets us to Friday's lab. And I think what I want to do is, for the last little bit, I will focus on Friday's lab. Let's go ahead and look at your notes just a little bit, or not your notes, your Moodle. And we'll go down to the next assignment on modularization. This will be modularization 2. And on this, we're going to write a program that prompts the user to enter a fraction as n all over d. And we will create a program that will allow us to add fractions, subtract fractions, divide, and multiply. So that's where we're going with this. We're even going to create a method which reduces the fractions. So this is where we need to go. In prep of this, let me go ahead and just create a real simple program that allows you to add two fractions. Okay, with that, I'm going to conclude this tutorial.